you know, which are the possible pieces? I don't know what. Okay, we've got a hypergraph which could be original axioms.
Yes.
Then, okay, so let's look at the rules of entailment. They're basically two kinds. Either statement 1 plus statement 2 goes to statement 3, or statement 1 goes to statement 1, 1a, query question mark plus statement 1b. Right, so in one case, that's essentially, I mean, that particular one let's see. I don't know whether these assume that these statements define. See, because there's a very non-trivial piece, which is when does an equality turn into a transformation? Because what we naturally define is a bunch of transformations.
Yeah.
But I don't think that's what. Yeah.
What does an equality turn into a transformation?
Look, I mean, the fact is, most of what we have in sort of mathy stuff is equalities of the form x per 1 equals x per 2.
Yeah. Yeah.
I'm still okay. So without time, there would just be an ocean of syntactically correct statements, which could include 1 plus 1 equals 17.
Sure. Right. We've discussed this before. Sure. Because it's just syntactic.
Right. But the whole point is that out of this emerges a set of kind of consistent a set of consistent statements somehow. These are the statements that can be, that the entailments right. I mean, again, there can be disconnected parts of math space, mathematical space, that are not connected by time evolution.
Right. Sure.
So, I mean, okay, but then okay, look, there are regions connected by time evolution.
Mm-hmm.
Which also, I claim,
Mm-hmm.
which also connect definitions, I claim.
So what do
So
you
in other
mean?
words,
Yeah, what do you mean? Yeah.
so what I mean is, if there's an atom,
Mm-hmm. Mm-hmm. Mm-hmm.
I don't know. Okay, so look, rules of entailment. So another big question is,
Wait. What do you mean by they also connect definitions?
well, here's the question. So let's say that I have a, let me think about this for a second.
And what do you mean by a definition specifically in this
Okay,
case?
well, so a definition is
Is it semantic?
no, it's just a name. Definitions are just names for things. But what a thing is
Mhm.
is non-trivial.
Okay. Okay.
In
So
other words,
some syntactic ontology.
yeah, but I mean, look,
Yeah.
a thing,
Mhm.
it's like in an immutable system,
Mhm.
things are better defined. By the time it's mutable, it's quite hard to define a thing. For example, in that multi-way systems based on numbers post,
Yeah.
defining a thing,
Yeah.
e.g., in 2 + 2 = 4, where does the first initial 2 as a quotes thing go? Is it destroyed, or what happens to it?
So is the immutability of a system basically the way in which it respects definitions? Is that what you mean?
Well, I mean that nothing ever, if you nothing is ever changed. If
Yeah,
something
that's
is,
what I mean. I mean, with transformation, its transformations respect definitions. The transformations don't transform the definitions. They can do other transformations, but the definitions stay intact.
well, what this means is, yes, because they're always just sitting there.
Well, they're not just sitting there, they're kind of carried along in some way. They're preserved. They're not
Well,
destroyed.
they're not changed.
I know, but it's something that's evolving. So it's not as though they're just sitting there. They're kind of carried. They're preserved in the
Well,
transformation.
maybe. I mean, this is the question of whether the definition is kind of directly burnt into the expressions, or whether it is separately carried along. And so one of the questions here is, how are definitions entailed? That is, we can have two statements that are in this relationship. That is, this is typical ATP format, where you take two results and you combine them to get a third result.
Mm-hmm.
Now, okay, so simplest definitions, names for names for statements. It gets a little bit more complicated. Oh, I see. I hope I'm not getting sick. This would be very bad. If I think I'm getting sick, I should put on one of these temperature patches so I can measure my... See, I'm actually a personal analytics nutcase. At least I have the stuff.
Well, without it, you couldn't even indulge your nuttiness, I suppose.
Yeah.
But I mean, even where I am, people are coughing and sneezing quite often, but I just imagine it's because of the temperature drop and not because of COVID. This is the thing. People are very sensitive right now because of the pandemic. People also just get colds. People used to get colds all the time.
Yeah, but it's hard for me to get a cold because I'm not really around people very much.
Right. Wow.
And that's what I was going to do a big analysis of. I've got all the data on when I've gotten sick in the last however long. And I just need to analyze it. Okay.
Now, so here, let's take this as an example. So you're thinking of definitions at, because I can imagine this at different levels of granularity. So let's just take the ring axioms.
Well,
you're thinking of definitions
what's
where
the plus? What is the plus? We're calling that plus. That is just a head of an animal, right? But the fact that the plus is the same plus in all these different pieces here. Okay, so let's take these axioms and let's make a let's take those.
Yeah.
And
okay.
Let's just say first of all of those. So let's get rid of the for alls. No, that's not what I wanted to do. Oh, okay, last of all of those. Okay, there we go. Okay. Now what I want to do is treat those as a graph. I want to treat this whole thing as a graph.
Yeah.
Okay, so what I want is to say, okay, so what I think I want is, let's take the first thing in there.
Yep.
Okay, there we go. So now, aha, you see, this is non-trivial because those two circle pluses are, all right, so what I really want is expression tree of %79. Well, let's just for the sake of.
Well, you could just make the notebook bigger. You take a look at it. Well, okay. Yes. Okay.
Okay, so this is. Now notice that these different instances of circle times have to be distinguished here.
Yes. Yes. Right. Well, If they weren't, you could only ever have one. Your axiom system could only really include one. Yes, yes.
What do you mean? I mean, so what I could do is I could say this defines a graph, and like those two circle pluses could be the same, but that loses information.
Well, that's what I mean. I mean, imagine if you could only use it once, then the axiom would be very simple. It'd be too simple,
know.
probably.
But what this is basically telling us is this circle plus and circle times, these are like atoms of space. They're like tagged atoms of space.
Okay. Okay.
And the ABCDs, well, let's see, the function nodes are like tagged atoms of space. The variable nodes are more like anonymous atoms of space. But now the question is, how do we make use of?
Wait, no. Hold on. What do you mean by anonymous? Precisely.
Well, this is what's complicated, because the fact is that we're trying to use one of these things that is an equality, right?
Yes.
We're trying to say that that reads against a particular other equality to generate a third one. Okay.
Yes. Yes.
And so that's why I'm talking about equalities turning into transformations, because we're saying there's something rather special about one that happens to have the equal tag there.
I understand. Yep. Yes, I understand. There's something kind of analogous in homotopy type theory, but it's not granular enough to be exactly what we're talking about.
What is it?
Well, it's basically that you have these groupoids and they're composed of this kind of intentional equality. And once you have that, you can perform group actions on the groupoid by basically taking functions over these paths, which are themselves equalities. So that's how they do it in homotopy type theory. You think of a function acting over the equalities as a groupoid action, but it's not granular enough, I think, for what we're talking
But the
about.
groupoid action is just, I mean, equality has all kinds of reflexivity and transitivity properties, right?
Yes.
And those properties become presumably properties of the groupoid. Like transitivity is presumably some kind of associativity in the groupoid. Is that not true?
Well, yes, I imagine so. Like, because you can concatenate these paths as well, between your different terms, and then you could start to think of it that way in terms of the transitivity or associativity of those concatenated paths.
Right.
But I don't want to necessarily lead us astray, because I feel
I understand, but you're saying in this case there is a, what is it, intentional equality?
Yes. So an intentional equality, all it means is that you have, different terms, say, of a type, right? And you can, say, determine that they both construct the same thing. So they're both inhabitants of that type, and if you can demonstrate that, you have some path between those terms, and this is how you get the spatial structure. And so in our case, I only bring this up because you're asking a similar question about, you have equalities. We're taking the transformations themselves are yielding other equalities, but we have equalities that are basically in the states, but then we also have some equality that emerges out of the transformations. and understanding what the difference is between those
I know,
two.
that's why I was talking about equality turning into transformation.
I'm just recapitulating to make sure that we're on the same page.
Yeah. But yeah, this is exactly the same thing we talked about here. Two forms of knitting. I don't think there should be two forms of knitting. I think
I mean, there are obvious differences between these kinds of between the transformation and the equality. I mean, in the sense that the transformation can destroy atoms and it can create new ones, whereas the equalities that are just in the states, I mean, they inform the structure of the states themselves, and that's quite different.
yeah. Well, that's the difference between a predicate, an abstract predicate,
Yes.
and you know, there's kind of symbolic equality versus action equality. Is like
Yes.
abstract predicates versus predicates with built-in meanings. Okay, but the big picture here, and the reason I want to see this empirical metamath stuff, that gives us an example where we can think about there being kind of a whole soup of initial, I mean, again, we don't know where to start. We don't know when, you know,
Well, you want to start with metamath, but maybe that's not what you mean by where to start.
yeah, I want to start by the thing I wanted to do for a couple of months now, which is just look at its initial corpus I mean, corpus, I just want to see for all of MetaMath or for a big library or even for a small library, what is its complete collection of math statements? Okay, so then given, okay, so empirical case. Look at complete collection of math statements in the current state of the library.
Now, you said something before about like 1988
Yeah.
metamath.
Right.
Is it that old, or
I think it is, yeah.
but can you access?
Yeah.
You can
Sure
access
access
1988
I'm sure you can
metamath.
access history. I'm sure we can.
Okay.
Maybe even the things that have been added are sequentially numbered. I have no idea.
Okay. Well, okay, we can find that out.
Right. But the question is, how much of the current state is, quote, syntactically entailed with no new definitions? Do you get what I'm saying? Right. So, e.g.,
Yeah.
in Boolean algebra, you know,
Sure, there are no new definitions in Boolean algebra.
well,
the
that's not
point.
obvious to me because there may be newly named theorems in Boolean algebra. As a practical matter, okay, so we can enumerate true statements. Okay, so hold on. Without having any more definitions.
Now, just to make sure I understand, if it didn't have any new definitions, what would that look like?
I'll show you.
Good. Okay. Mm.
Okay.
Okay.
I'm just thinking about this for a second. Okay, so this is okay. So this is expressions as opposed to statements.
Yeah.
Oh, okay. So this is the syntactic version of true statements of statements of logic, right?
Mm.
Um, okay, so this is of those.
Hmm.
We can ask which ones are actually true statements based on the axioms. But we have a different approach, which is we could just say, okay, this is logic as logic now using logic as logic has developed.
Logic has developed.
With its standard axioms.
Yes. Yes.
Okay, so the
yes,
alternative
yes.
is, let's just pick any set of these as axioms, right? Alternatively, just pick any set of syntactic statements and start seeing
Mm.
what statements they syntactically entail.
Well, yes, this is the goal. This has been the goal as I've understood it.
Right.
This
So
is
we
like a
just pick a subset.
meta modeling exercise.
Right.
Yes.
So we just pick some subset from here. arbitrary subset. So for example, if A equals B is in there,
Yeah.
then we're toast because everything's going to be true. Right?
Yes.
It's not a very interesting theory at that point.
Right. Yes. Well, that's come up so far, even with the code that Nick has developed. A equals B and this kind of thing. A and A equals B, or not and, but dot operator. Yes. I mean, you don't get anything out of it, really.
Right. Okay. But so,
or alternatively, you're saying you get everything out of it.
yeah, right.
Same thing. Yeah.
Right. But so the whole point is, in the entailment rules, let's pick an example.
Yeah. Great.
Like A equals A or A. And A.
And yeah. Yeah.
Okay, hold on. So the A here
Yeah.
is replaced by a unique atom.
Wait, which A here?
They're all the same. They're all the same.
Okay.
Unique
Okay.
atom
Okay. Yes.
when the entailment transformation is made. Okay, so this means that, or put in a different way,
Yeah.
that's saying that this thing is ultimately A blank
Yep.
double equals
Yes.
A blank is transformed to module A
Okay.
something like, wait, hold on a second, hold on. Yeah, it's something like this, because in the end, oh, clever creature, right? It's saying those conflict because they actually can't be the same atom. Because that's going to be a, again, like this.
Yeah.
Okay, it's always different. It's always a different thing. So that means we are just eliding things by using the same variables there. But
Right.
the and operator is the same.
So it respects that definition. It's immutable.
Well, no, but I'm saying
and.
when you make an entailment transformation, you are changing those variables to completely new and fresh variables.
Yeah.
But, and so what I'm claiming is, you know, the variables are just atoms like this, but the, you know, the operators and constants have persistent names.
Definitions?
Well, i.e. their definitions.
Well, what's the difference between name and definition?
I don't think there is one.
Well, then let's just say definitions for purposes of consistency. Okay. Okay.
So,
well, good. Yeah. So this transformation respects operator definition. So it's immutable in that sense. Okay.
Yeah.
Okay.
But then we have to know what are the laws of entailment. That is, given two expressions, what can we actually do? Right, and the laws of entailment treat equality in a special way.
Yep. Yes.
That is, there's a built-in symbol in some sense that represents the equality operation. I don't think it's, I think that's right. I'm not sure if that's actually correct. And I think my understanding of MetaMath is that its update rules are very, very structural. And possibly so structural you don't even need that. But okay, so this is a big question. This is a question for what are the laws of entailment? Right? What are the best laws of entailment given the symbolic representation of things? But again, what's fundamentally going to happen is the laws of entailment are going to cause some ocean of symbols or ocean of expressions to generate some different ocean of expressions.
And what's the difference between the law of entailment and just the rule that's guiding the transformations?
There isn't any, they're the same thing.
Okay. Can you include that as a note? I'm just trying to
right.
But want to make sure when I communicate this to Nick that
okay.
he can understand.
These are the built-in meta logic transformations.
So this is not that dissimilar from the physics project in some sense.
That's right.
In some sense, yes. Okay.
Because there is a meta logic to the physics project, which just says you look at a hypergraph, if it matches, you do the transformation. That's its meta logic.
Yes. Yes.
Okay,
Yes.
so I'm looking for a similar meta logic here. And except there's a difference because in mathematics, you sometimes think about the axioms. I mean, this is the meta logic below the axioms. The axioms are just being wheeled in every time they're needed.
Yep. Yep.
And it's a little bit unclear to me whether the axioms are like monoclonal antibodies.
You'll have to elaborate, Stephen.
Well, because in the sense that they keep on getting replicated.
Oh, okay. In that sense. Okay.
I mean, in other words, they're not. One theory would be, it's like the immune system and whether you have memory B cells or something, whether you have a single cell that sticks around,
well, no, you don't think that's the case. You don't think that there are.
I don't. No, I think it's the same thing as happens. And it's probably the case in mathematics too, that each okay. So in physics, for example, okay, in mathematics, in the progress of mathematics, one may be continually regenerating quotes the same statement, except that it has different atoms in it.
Okay, so the atoms are fresh and the operators are respected under transformation. They're preserved under transformation.
I think so. E.g., differently named variables. Now, is there an intermediate case? Could it be the case that the operators can evolve too? See, I think it could be perhaps the operators can evolve and and the perception that the plus here and there is the same is a matter of observer and reference frame. Perhaps it's an important feature of a reference frame that it thinks that all the pluses or all the ones in the universe are the same. That's a piece of equivalencing done to make it easier for to understand. That's part of what the mathematical observer does.
We do that.
Yes.
Yes.
Does the mathematical observer conflate all the twos in the universe? And no doubt the answer is yes. In other words, the two I just got by computing 1 plus 1 and the two I got from computing 5 minus 3, why they're the same two. That's us doing that, I think, to say that they're the same two. Now, okay, now what about the plus side?
Well, what about like with reflexivity though? Like 2 equals 2.
Yeah.
I mean, on the one hand, you can say, well, they're the same. That's why we have reflexivity. But on the other hand, you could say, well, you have to be able to distinguish them in order to be able to express reflexivity at all.
Sure. Right.
Now, wait, there was this other question, which is operators, strange cases in which operators actually change.
I don't think it's that strange. I think they just change. I think that the fact that I think that the identity of operators is again probably a reference frame thing.
The identity of the operator.
Right. The fact that it's the same plus.
So plus equals plus, and that's a weird,
Well,
weird way of
like if
thinking
I
about
say
it.
x plus y, if I say x plus y minus z plus z, okay, what is that plus? Is it the same as the plus that I had here? Or if I say 2x plus y minus x, is that the same plus? Is that any more the same plus? Well, this is algebraic variables, which are even a different can of worms.
Right. Right.
If that was a function, then let's see.
We haven't really discussed functions yet, how exactly they fit in here.
Well, I think they're part of the entailment. It could be that every one of these things is the entailment basically thinking about you know, yeah, I mean, this is the same claim, basically. Given axiom system is operating in a particular rule reference frame, is the same claim as the claim you're just picking out random. You have some connected component that you're picking out from the entailments of some set here. Given a particular set, it has certain entailments.
Couldn't you have a function? You should have a function in a state. You can do an entail because you can have functional equations. I mean, you can also have,
Sure, but the
functors and this kind of thing. So you can, you can take a function as an object in some way, or some mapping as an object.
But
so it
the
doesn't
problem
necessarily
is
have to be entailment. Yeah.
Okay, so look, this equality, some point this has to engage with a meta logic, and this equality either has to mean something or just be a purely syntactic thing. Now, what if it was purely syntactic?
Yeah.
It had certain axioms. Right, so that's supposed to be true of equality.
Mm-hmm. And are we thinking about this as an entailment?
No, I think we're thinking about this as just a random. Boy, hold on. What is this? Well, that's a constructing one thing from another.
Via transformation?
Yeah, I think so. But I mean, that would suggest that
okay.
every one of these equalities is actually an entailment.
So then you get that equality though through multiple transformations, and then it's in the state, right? And with time,
so.
it achieves some semantic quality through the transformations, even though originally you just have syntax, you're performing some meta logic over it.
See, the thing is equality as it appears in an expression special?
Special.
Well, I mean, is it a look? There are random predicates, right? You could just have a random predicate P, and predicate logic just tells you how to transform that predicate P.
Yep. Mm-hmm.
Okay, I mean, the basic point is, in the meta logic, transformation is special. Heraclitus would be proud.
Finally, you can stop crying and be proud of something. Yes.
Right.
Well, but what does special mean besides amusing to Heraclitus? What does special mean?
It means that it is a thing without further definition. It's a thing that just happens.
It just happens, but it can respect definitions and it can give rise to some sort of semantics as well, right?
Yeah, it gives rise to semantics by virtue of connecting things.
Which
it,
is
quotes, just happens. CF, Heraclitus, and Leibniz. You see, this is what, you know what I should do? You know, all these people who are saying, you know, all these things should have references. At least we can get, you know, problem is it's hard to cite Heraclitus because
well, there's the fragments. No, Oxford has his fragments published, I believe.
Okay, yeah, that sounds about right.
Let me check.
Okay, but I mean, this is the point. This is kind of pattern matching change.
Yes, it's Penguin. Penguin published his fragments. Anyway.
Okay.
Add that to your library. Okay. Okay, no, okay. So transformation is special. It just happens. Well, this is also the case in the physics project. This is the point.
I know.
I know you know. I'm just making sure I understand. Yes.
Yes, that's the point. Transformation just happens. And transformation is the progress of time.
So time has this semantic kind of residue or consequence then here.
Yeah, I mean, transformation is special and it is the passage of time. In physics, in our perception. So in mathematics.
Well, but that's what's the difference between mathematical perception or observation and just semantics? Is it the same thing? Is semantics basically, is that your foliation or your reference frame?
Yeah, I think so. Because I mean, basically what this means, okay, everything will just be floating freely in the ether, you know, without transformation. Things are without form and void, or whatever the phrase is. But I mean, without transformation, all the possible statements are just floating separately. Transformation is what knits them together.
And that's knitting. Is that the only kind of knitting?
Yes.
Okay, so there's just one kind of knitting, and it's that.
I think so. Yeah.
Okay.
Transformation is what knits them together, and because it takes okay, but this is then this is a part I don't fully understand.
Okay. All right.
As how important is the role of shared atoms? I think it isn't important at all. I think it's just a convenience. Because, for example, in that most recent post, there aren't any shared atoms. Well, numbers are just such a frigging mess. Because, you know, in a picture like that, right?
Yeah. Yes.
Right. This is all about equivalencing.
Right.
And
Right. Right.
right, we could tree it out completely. But we're saying the first line of defense of the observer is not to do that. In other words, in principle, we could tree everything out.
Yes. We could undeduplicate or simply duplicate. Is the question whether or not the transformation is the same in either circumstance, with it treed out or not treed out?
No, I think the transformation is the
It's
point
same.
is
Yeah.
that you can end up with two completely different collections of atoms of space, but they're deemed equivalent.
Mm-hmm. Yes. Yes. But is the question?
Yeah.
Well, you see here, are we starting to approach this continuum limit question?
I don't think so. I think the issue first is, look, in the most simple-minded form, every different derivation of 2 + 2 = 4 is a different expression, is a different state slash statement,
Yes.
right?
Yeah. Yeah.
But the first role of the observer is to conflate equivalent forms, is to conflate, quotes, relabeling equivalent forms, which means isomorphic hypergraphs, which means whatever else.
Mm-hmm.
Okay, now the reason 2 + 2 = 4 is weird yes, the reason that's not quite right, okay, let's go back here. I'm going to have this expression.
Yeah. Yeah. Yeah.
Consider chump, okay?
Yeah.
This
Yeah.
is basically meaningless unless you know what that plus is supposed to mean. This is useless without knowing what. So I'm saying, in essence,
Well, let me understand what that means. So you're saying because under transformation, the variables are going to change, and if the operator isn't preserved, then nothing's preserved, and then you don't have anything.
Yeah.
Right? Yeah.
Yeah.
That's the point.
Yeah.
Then,
but I mean, but the
yeah,
whole
okay.
thing is that the transformation should be preserving the operator, probably.
That's the point. Yep.
Right.
That's
And
the
so
point.
that means that
Yes. So you're saying without knowing what the operator means, basically just means that the
the operator was
transformations are
created at
preserving
some
them.
point in history. And once the operator is created, it probably just gets infinitely grandfathered.
Yes. Yes. How does it get created? What's the genesis of the operator?
in the beginning, there were all the operators, and they were named, you know.
They were named, and then those names were respected under transformation.
There isn't any
Okay.
new idea under the sun, as it turns out.
No, but something less apocryphal. Like, no, but seriously, I mean, and I mean it in terms of the transfer. Like, you begin with something. Does that mean you have to begin, like, if you're generating something with transformations, you have to begin with all the operators?
Yeah, you see, I mean, it's an interesting question. Whether how does an operator come to exist? How does times come to exist from plus? How does plus begat times? Beget. Okay, so we have A plus A plus A plus A plus A plus A. And then we choose to name that. You see, that's just a human thing that we're naming it times.
Right.
So the question is everything ultimately reflect down to the Ur operator, so to speak?
Reflect down.
Well, I mean, does it, the fact that we now call this, you know, look, it seems like an observer determined thing to call this times 5 comma A.
Yeah, sure.
It doesn't seem like something that's fundamental.
But that means that the observer is doing more than just conflating states. The
Oh,
observer
no,
is
we know the observer does much more than conflate
okay,
states.
so the observer also, in some way, I don't know what you want to say, but miraculizes these, I mean, creates these operators.
Well, yeah, because that's how we're choosing to talk about things.
That's interesting.
We choose to conflate. First of all, we choose to conflate all the twos in the world.
Yes.
Then we choose to have a notion of times, which we don't have to have. I mean, in pure arithmetic,
Right.
we could just have, you know, a bunch of successor operations. We could compile everything to successor operations. Right. So we can compile. I mean, that was sort of the Whitehead-Russell thing. We can compile everything to very simple atomic quotes logical atoms. Actually, better, aka releological atoms.
Sure. That's not, I mean, that's obvious that you can get, you know, times from plus, and you can get divides from times. That's all perfectly fine. You can get exponentiation from,
right, but that's not how, but how does mathematics actually work? What mathematics does is, this is part of, mathematics is not a molecular dynamics.
Right. Yes.
Mathematics is making use of the fact that we've built these kind of towers. Okay, so the question then is, let's see. Okay, the raw mathematics. You know, here's the point. The raw mathematics just says we have a binary operator.
Good.
Right?
Well, but of course, you know, and that's the real operator, of course. Where that comes from, we can get into that at some other point.
Oh, that's just syntactic structure. So we can think of that, you know. Okay, so we start with that from an abstract binary operator.
And you're saying the other operators that we get, they're like these containers or these foliations, if you will, in which we're observing. In which
I think
we're
so.
performing
I mean, I
mathematical
don't think there's
operations.
anything.
Yeah,
We start from an
no,
abstract binary
that's fine.
operator,
That's
and
fine.
the fact is, and this, just like variables,
Yes.
this gets transformed to another abstract binary operator. But like variables, okay, so now how does this work? How do we know the equivalence between, see, with variables, all right, with variables, we know that f of AB, f of BA, like this, is exactly the same as f of C, f of DC.
DC, yeah.
Like that. Right?
Yes.
We know those things are equivalent.
Mm-hmm. Mm-hmm.
But it isn't the case normally that we would say that this is equivalent. Normally we wouldn't say that because we think that f means something. And the same with a constant here. If we we also don't imagine that f of a x is equal to f of a y for constants x and y. What the heck is an operator or a constant? How does it?
Good. Okay. Yeah. These are the right questions to ask. What is an operator?
So expressions are equivalent if they have the same topology, effectively. There's a topology of expressions, right? So expressions are equivalent to the observer if they have the same, well, actually tagged topology, i.e., variables can be anything, but constants and functions, constants and operators have to somehow follow the tagging. I wonder if this is related to causal graphs.
Could be.
I wonder if follow the tagging just means causally connected.
Well, you could think about that for times and for addition and multiplication, for instance, right?
Yeah, I'm wondering. I think it may be the
You
case.
get to the same result using addition and multiplication, for instance. It just takes more steps for addition.
I know, but the same operator might just mean causally connected. Okay, let's see how that would that would mean in terms of token event graphs.
Okay.
So
okay, good.
It's a little unclear to me how you derive tokens. See, a token is that which is transformed.
Yeah. I know it's tempting to just call operators events, but that's not right. I'm not sure that that's right.
Okay. I don't think that's right. I don't think that's right.
No, I don't think. No, I'm not saying it's right.
Okay, but the question is, what are the tokens? And the tokens, it's somewhat complicated because, as we can see from the theorem prover, the substitution laws operate on these expressions in slightly complicated ways.
Yeah.
Let's see. Okay, still trying to understand this.
My only concern at this exact point we are is I feel as though we're trying to answer quite a few questions at once. It's not clear to me which exact. I mean, there's this question you've written right here, but I feel as though I'm juggling like four
Okay,
questions
but
or so.
I think that there are two basic things to do. Okay, I think one is the empirical work on metamath. Okay, which I think is going to be quite revealing.
Okay.
Not least as you won't be able to do it until you can answer some of these questions. But I don't know which of these questions exactly you have to answer. Right. So what it's going to be, it's going to be a boatload of definitions together with just random statements. And I mean, I think you don't ultimately need any definitions at all.
What about
the question is,
what about for the operators?
I think you need causality. I don't think you need definitions.
Okay, so we don't have any definitions. The variables, so to speak, will change, transformation. The operators, we don't necessarily have to think about, I mean, we've been speaking about the operators basically being preserved under transformation, but you're saying there's some other way of looking at it where it's basically some sort of causal invariance, and it's from the causal invariance that we get operators.
Well, I'm not even saying necessarily invariance. It's just a causal connection between that F is causally connected to this future F. I'm not sure that's right. I think what has to happen, I mean, this question about the genesis of operators is an important question. Do operators persist, or are they merely equivalents together? It just seems much more natural. Okay, we're saying the expressions are equivalents together just based on their structure.
Their structure.
Yeah, they're isomorphic hypergraphs, for example.
Well, okay.
But the names of their nodes are all different.
Sure.
But I have to say, I think the answer is going to be that the operators are simply connected by causal connection. Operators are conflated. Okay, so my claim.
Can we draw this out?
Yeah, possible claim. Operators are conflated if they are causally connected.
What exactly does that mean, though?
That means one of them was made from another, as opposed to just being brought in deus ex machina, so to speak.
Well, but they still had to originate.
That's okay. I mean, there's a soup.
There's a soup
Of stuff, of an infinite set of possible things.
Yes.
You're basically just mining a different part of the Roolead. To wheel in a new operator, you're just mining a random new part of the Roolead.
And you're looking for some sort of causally connected thread.
Yes. Yes. To make.
Well, that's fine.
To make a new operator,
That's fine. Yes, I understand.
just
that
mine
actually.
a new part of the Roolyad.
Mine some causally connected.
Well, eventually it's going to be
Thread of-
causally connected, yes. But I mean, you're just fresh. Okay, so what does it mean? So what we need is a toy version of,
So yeah.
now look, let's just try and construct a toy version of this operator. One thing that's kind of icky is that these things are trees.
Yeah.
We can turn them into pure hypergraphs.
Yes, we can.
All we need to do is make them into Lisp, basically.
Well, Nick has something where you basically have trees and you can get hypergraphs out of them.
Okay, so I would claim that this turns into the hypergraph f of b x combined with the hypergraph x. No, actually, that's not right. I want to have how the heck does one get this? I'm not sure how to do this. Right, that's a technical question. How do we turn what we normally think of as trees into hypergraph-like elements?
I think
then,
Nick knows the answer to that question. I think
Okay.
Nick knows how to do it. He has some kind of rudimentary way of doing it. He has some way of getting hyper edges.
Okay, well, you should find that out. Okay, so then what we want to do, okay, what we want, make derivations in several toy theories. That all involve binary operators, all involve, say, a single binary operator,
Okay.
e.g.
Group theory.
NAND calculus.
Or NAND, that's fine.
Group theory has other junk in it. Semi-group theory.
Okay.
Even that isn't.
Maybe not. Maybe don't start there.
Well, no. What's the name of the thing? A semi-group without identity. Is that a monoid? Does a monoid have identity? I'm always forgetting. We can just look it up. That has identity. Actually, what we need to do is just look at axiomatic theory. And now here, for each of these, we need to know, like the, I don't know, Meadow axioms.
I believe quasi-groups and semi-groups don't have identity.
Yeah, hold on, we're going to find out another thing here. Oh, I see. We're considering that the identity is in there. Okay, so what we want to do is we want to select in axiomatic theory for axiomatic theory of hash. I love things being computable. What do you know? There are all the axiom systems that, in a sense, live in the same syntactic space. Right. All these live in the same, quotes, operator semantic space, syntactic space. They all involve just a single binary operator. Now, interestingly, some of them are actually the same theory. Some wind up being, quotes, the same theory, though differently stated. Others are different theories. See what I'm saying?
Yeah.
The central groupoid axioms surely do not generate the same set of theorems as, so for example, let's do the following. Let's say groupings. Let's see, Nick also has the thing for finding models, doesn't he? He has this find model.
Yep. Yes, he does.
What is that thing called?
What, to find the model?
Yeah, finite models or something.
Yeah, look at it. Let's see. Nick was just telling me
Find
about
finite
that.
models.
Oh, okay, you got it.
Okay, so let's take this one here. Look at that. Coolosaurus. There's a couple of finite models for that thing. So now, okay, I don't know what those numbers mean there. Beautiful. Beautiful. Okay. So this is finding finite models. So that's a way to determine whether two axiom systems. So for example, if we were to take two axiom systems from here, which are both supposedly axioms for Boolean algebra, let's take those two axioms.
Okay. Okay.
And let's, for the hell of it, let's put in the Sheffer axioms as well.
Okay. Yeah.
What does that mean? I'm confused. Why are those not giving? Oh. magnificent. Nand and Noor, our friends. Here, they'll all be blank because of Stone's theorem or whatever it's called. I should have parallelized this. Okay, well, anyway. But okay, so these axiom systems are equivalent. And also in a different world, we can say find equational proof of axiomatic theory. Let's say my axioms from
Yeah.
That was fast. Okay, dandy. So what this is doing is there's hypothesis. Right, there are the axioms. There's the hypothesis. And we're trying to use the 2-to-1 rules to derive true.
Okay.
So meanwhile, the other thing we could try to do, let's see, this is deriving that. What was the other thing we were going to do? We were going to try to derive. I think that this find equational proof has some base axioms in it, like the equality axioms. I don't think that this can actually get anywhere if we replace the equality by something else. It needs that.
Right.
But okay, but here, what we were trying to discuss is whether these operators. Let's take this equivalence here. Okay.
Yeah.
In some sense, we have established that those operators are the same.
Okay.
The operators which appear in those two axiom systems are the same. Whereas,
Yeah.
if we just say, let's say we try to prove the central groupoid axioms.
Yeah.
It's going to say no dice. After taking a very long time. Right, that's because there is no equivalence. There is no entailment causal connection between the expressions of the Scheffer axioms and the expressions of the central groupoid axioms.
Okay.
i.e., these are disconnected and in metamathematical space in the history these are disconnected in the sense that there's an event horizon between them when the dynamics is entailment. Now, in a minute, we're going to talk about axioms that can do universal computation.
Okay.
Because they should be able to get to anywhere.
Right. Though
These are black
apparently,
holes. These are basically black hole axioms. You can't get there from here, so to speak.
they're not. It's not that the axioms are black holes, but there's some axiomatic black hole.
Yeah, it's a metamathematical, i.e., these axioms live in metamathematical black holes. You can't get out from that axiom to something else. Okay, but the issue of whether this is exactly a story of causal connection. That is, two atoms. We have this technical issue about expressions versus hypergraphs, which we need to resolve. And we need to know exactly what the substitution, well, I think the substitution thing is just like it is for hypergraphs. In the hypergraph case, we're just saying, does this hypergraph match this other hypergraph?
Yeah, okay.
And it's just exactly the same thing. In other words, all we do in one of these, okay, so I claim what we do here is we take I claim all we do so I'm going to make the claim that what we do is this. I think it's that. Except the only exception is that equal sign. And what I'm claiming is yeah, it's a little tricky in our language because of the fact that it's blank on the left. And so then we have to resolve this. Okay, this has to resolve. Boy, I have to say, and some things one's lucky and some things one's not. In the definition of the evaluator for SMP was so incredibly lucky because it's so it threaded its way through so many horrendous issues. The one thing it didn't get here, well, actually, SMP did this better than modern Wolfram language does. SMP didn't distinguish between pattern variables and Okay, so SMP did not distinguish $X on the LHS from $X on the RHS. See what I'm saying?
Yeah.
So in SMP
Yeah.
land, it's f of $X colon $X squared. See what I'm saying? So it didn't distinguish the pattern variable on the right. Although there's a million reasons why it's better to distinguish the pattern variable on the right, but this is a
But
case
in this
where
case, right, yeah.
we're getting a little bit toasted by that.
Stephen, I have to take a 1-minute break.
Yeah, I also should take a break and get some food here. I'll be right back.
Okay, good.
Hello there.
Hello.
Okay. So we can imagine in the Roolead a C of all possible transformations. But there's this very weird thing. I still don't understand the relationship between the expressions and the transformations. I see. One possibility is or a sea of equality expressions. And then the entailment is just the application. Okay. So then one equality to another.
Yes. 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 That is right. That makes sense.
Right. So let's take the minimal version of that. F blank so what is the entailment? So let's say we have F this is that's an equality.
That's an equality, right?
Okay, so now let's say we have something like well, we need to.
We're going to take some transformation of that.
Yeah, what's a theorem? That I think, is this a theorem based on that? When in doubt. Okay. So then I'm now confused again because
yeah.
one thing we can do. See, I'm confused because that. How do we derive? Oh, I see.
Yeah.
We should be able to derive that second thing from the first thing.
Well, sure. Let's look at, if you want, we can look at the proof graph. You can see how.
No, I understand, but I mean, oh, I see what you're saying. This is so freaking incomprehensible. Do you understand what this is doing? Oh, I see. All it's doing is flipping around that top level thing.
Yeah. And when you do that, then yeah.
Done.
Okay.
So, but in terms of our model, though, well, it's the time dynamics. We start with this. This is different time dynamics. This automated proof is not.
Yeah. Do you mean when you say time dynamics, do you mean just the number of transformations?
No, the nature of this proof is this and this together derive true. This, I mean, it's like we saw in that proof graph up above. You
Yep.
can
Yeah.
you can derive true by the implication blah 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 implies blah 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 is equivalent to true.
Mm-hmm. But how does this relate to the idea of these transformations that we're discussing?
It's a 2-to-1 transformation. Two of those,
Yes.
every step there's a 2-to-1 transformation.
Okay. True. Okay. We get true, we get it semantically, we get it through the 2-to-1 transformation.
Yeah.
Yeah. Okay.
Look, in this case, we're modus ponensing it.
Right.
We're saying this
Yep.
implies
Yep.
this, as opposed to, you got this whole kind of human overlay. Okay, so we've got, those are our two special operators, probably. And we could add not for good measure if we wanted to.
Now, what's a special operator?
Something which relates to the meta logic.
Are they the operators? Is this what you mean?
No, I don't think so. I think that these are, I think there isn't just one way to do the meta logic.
Well, sure. Sure, that's the same idea from the physics program.
I wonder whether we can get a list of possible. Can we get a list of meta logics? Let's see. There's some article here about logical consequences. I don't really like the term logic, because I think it's much more general than logic.
Oh, yes. Yes. Are you sure that this would be helpful for thinking about this underlying transformation meta logic? I mean, it's supposed to even underlie and extend beyond our reference frame. Is it not?
Yes.
Well,
So what are you saying?
well, you might not find it in fact, I would suspect you wouldn't find it in contemporary mathematics because it's supposed to underpin it and mathematics in other reference frames. I mean, the point is we're going to try and find it, like in the physics project.
Mhm. Well, except that the end result is it's all possible transformations. That's the really hard story.
Well, that's a question, which is in the physics project. There's still the Roolead, but there's also this idea that we can try and find a rule for our universe.
See, here's what we're doing. Here's the philosophy of it. Okay. There are three entities: us with our brains, the universe, and computers.
But what's
Our
the
mission.
what's the universe for the MetaMath project though? That's my question. Yeah, that's the question I was trying to get at. I mean, we know what it is in the physics project. What is it here?
3 million theorems in the literature of mathematics.
Okay.
The best mapping we have. Just like 3
Yeah.
million theorems of a history of mathematics are like every telescope plate we've taken for the universe.
Oh man. Okay. Okay. Well, okay.
So our goal, I mean, our goal might be to find the laws of mathematics. You know, all right. In the physics project, given our human observations of the universe, the goal is to find laws of physics aka underlying rules consistent with those observations.
Yes. Yes.
Right? And
yes.
it might be that an alien's observations might lead to different laws of physics.
Right. And that's why they don't go on the peer review committee.
With some rule motion to translate to ours. That's in a sense what rule motion is about, is translating from one.
Right. But it might not always be possible, you know.
It has to always be possible because of computational equivalence.
It has to always be possible.
The one thing we know is that our universe, as all of our universe that we can ever have access to is computational equivalence. Okay, so now in the mathematics project, given our human observations of mathematics, i.e. 3 million published theorems, find the laws of mathematics consistent with those observations. And there may even be more to it than that. I mean, it's basically saying there is an inexorable character. By the way, the only way that you would not be able to convert between different universes is if one's decidable and one's not.
Well, that's what I got the quote. There's some passage from the Real Space blog, and you're talking about rho, right? You're talking about the speed of, or the rate. And you're talking about, well, what do you say? You say, quote, if from your starting point, you can follow a path that's irreducible and effectively universal computation, then you'll successfully be able to reach the other point. But if your starting point is reducible, it won't necessarily be true. And that's what I had in mind when I said that it's not always.
Yeah, okay, right. In other words, okay.
Yes, there's computational equivalence, but there's also reducibility and irreducibility.
Right. So you could rulily translate okay, so I think the laws of mathematics. Okay. Yes. Yeah, look. The laws of mathematics could be geometry or algebra or arithmetic or algebra. Well, actually not so much, not any algebra, etc. Okay. And so you can think about mathematics in terms of geometry, let's say, or in terms of arithmetic, etc. See what I'm saying? There is a translation between these, although it may be a lot of effort. Yeah, you see, this is analogous to, okay, in physics, we only have one physics. In math, we have multiple ways to describe the same underlying thing, underlying essentially Platonic thing. Which, by the way, which is always a slice of the Rulliad. But in physics, we've only got one slice that we're seriously talking about. Now, I mean, in physics, we can talk in terms of positions or in terms of momenta, for example. Position space, momentum space. Or I use different coordinate systems, canonical coordinates, particle content descriptions, etc. But those are, we kind of understand how to make those into convertible. In mathematics, we're slowly understanding, but the transformations are a bit more complicated. By the way, in physics, these correspondences are dualities. That's what people refer to those things as in physics. In mathematics, it's the ability to have different description languages. Okay, so then
yes, and this could be functoriality, at least if you have a category theory perspective of math. But this goes, I think this goes deeper than that.
Explain the category theory version of this.
Well, I mean, take the Langland's program, for instance. I mean, if you have the category theory of the categorical version of, you have one area of mathematics, you have some other area of mathematics, and if you have some functoriality between L groups and their automorphic representations, then voila, you've built the bridge between.
Right. Functoriality is motion in Rullial space.
Yeah. Yes.
I.e.
Well, I mean,
it's isotropy, and it's some kind of homogeneity, motion / homogeneity. The fact that you can do it, if the space wasn't somewhat homogeneous, you wouldn't be able to move from one place to another without huge, I mean, in other words.
But what do you mean by homogeneity in this case?
Well, I mean that the the structure of theorem space in one part of is somewhat similar to the structure in another part, which is to say that there's this correspondence between
right, okay,
one category and another. I mean, it's the possibility. Functoriality is the possibility of motion, i.e. homogeneity. I'm not even sure it needs to be Rullial space. I think it's merely maybe Rullial, or it may just be metamathematical space. Those things may actually be the same because of this business about equality being part of the meta logic. So that the transformations, it's all a little confusing.
Well, are we including equality in that sense?
I'm not sure.
I'm not sure either.
Okay, but in any case, so okay, what's the role of time? Without time, nothing is related to anything particularly. Time is what entangles things.
Yeah. I mean, I also think that with time, you get transformations and you get semantics. And that without time, you wouldn't have observation, obviously. You wouldn't have
It's
mathematical
the source
observation.
of entanglements. It's the source of it's making anything non-trivial. Without time, everything without time.
It's just everything's loose.
Yeah.
Yes. Yes. Right. Everything's loose and dissociated.
Now, one feature of time, one feature of the things we're describing is that there's some locality. You know, feature of the physics project, locality in the rules. But maybe that's self-evident. I mean, as soon as there's, actually, this is self-evident from finite information in the rules. In other words, if there wasn't locality, you could just say, okay, I'm just going to pick up, you know, random atoms of space from everywhere. I don't know. I think there's a.
What is everywhere in that case? What does that mean?
Well, for example,
Where?
well, for example, disconnected hypergraphs. If the left-hand side is a disconnected hypergraph, then you can go knit together parts of the universe that are completely unconnected.
Yeah.
Okay, but so the concept is, in mathematics, there is this notion of entailment, which is also the notion of proof.
Yes. And it's also just the transformation performed according to some metalogical, metamathematical rule.
Yeah, which we also call proof.
Okay. But without time, you couldn't have some rule operating on anything as well.
Right, time is entailment, which is also proof. And proof is what? Yeah, I mean, proof is what knits all this stuff together. And so then multiple parts of proof.
Yeah. Yeah.
Are let's see. What is the relationship to the infinity groupoid? Because that's constructed by looking at proofs between proofs.
Yes.
Getting to higher categories.
Yes.
What does that have to do with this?
With time.
What are you saying?
I said, you're asking what's the relationship between the infinity groupoids and time.
Yes.
Time is proof.
Well, I think the issue is there is in some sense of spatial computation, because in there is an idea. Okay, so this is okay. So one thing is, you know, versus higher categories.
Spatial computation.
So what I mean by that is, one thing is you deduce, quotes, later states
Mhm.
from earlier ones.
And what does that mean? I mean, that means you're performing some observation over time.
No, I'm just saying that you're applying transformations, right? But that's a little bit of a different operation.
We apply the transformation.
No. The transformations are applied.
Well, good. Yes. Well, that's what I mean when you're saying you're making observations, and you're being updated as an observer as the transformations are happening.
I agree, but I'm not sure that's the point I was making here. Was that if we make your average proof graph, so for example, we take let's take an example here. Our friendly example. This thing, okay? So now, one thing is that you take the proof, you take the chunk type thing, right?
Yeah.
But the homotopically equivalent paths,
Yeah.
how do we deduce the homotopically equivalent paths? That is ridiculous. Homotopically, I didn't misspell it. Wow, that is a spelling word. Let me send it in. Okay. How do we travel from one path to another? How do we go from one path to an equivalent path? Right, that's the question. To go down a path, we're just following the transformations.
Yes.
The
No,
answer,
wait.
I think.
Okay. Yeah. Okay. Go ahead.
No, I think we have to jump branch pairs.
Yes. Well, yes.
We have to go from one side of a branch pair to the other. We have to keep doing that. And is it not the case that any homotopically equivalent paths are found equivalent by just
Introducing a term of their identity type or proving their equality.
Yeah, but like if we take those two guys there, one way we could do it is just to jump from path to path by just saying at every node, flip the train tracks the other way.
Yes. But can we do that as observers?
I'm not sure we can, but I'm not sure we can make time progress either. I mean, it's just something that happens. I mean, this is a question of whether. Let's not worry about what the observer can do for a second. Let's just ask the question.
So when you say can we, you don't mean as observers.
Yes, I don't mean as observers.
Okay.
I mean just.
Well, yeah, then yes. I mean, if two paths lead to the same result, there you go. There you have it.
Right. But this homotopic equivalence of paths is probably not the same thing as cellular automaton spatial computation. This is actually This is not spatial computation. It's homotopic computation. It's path-to-path computation.
Mm-hmm.
As opposed to state-to-state computation.
Good. Okay. That's fine.
Be good to have an example of where path-to-path computation doesn't work. In other words, well, there's an obstruction from getting one part. I mean, just like state-to-state transformation. Well, it's pretty obvious, actually. You might not be able to get from one path to any other. Which paths can you get between? And so let's look at a case like this.
It's just difficult because this rewrite rule, it's not mathematical, so it's hard to
No, okay, fair enough. But which paths can you get between? Specify the path between paths by giving a list of branch pairs that have to be flipped. So for example, let's take this case. Okay, so let's say we're going from AB to BAA. Okay, so there we've got a path. Now, how do we get another path? Does find path let you ask for multiple paths?
that would be a nice multi-computational feature.
There you go.
Oh, it is a nice feature. Okay, we have it, right?
Okay, so that one is the first path. Okay, so there seem to be 8 paths there. Okay, so that one is the first path, and we're asking to get to the second path. Okay, there's just one flipperoo there.
Okay.
Right, so in other words, we can characterize the path to path between these two paths. And in fact, in general, let's see how we would represent these flipperoos. So what we're saying is, between each successive path, there will be a divergence point.
Okay.
And there might be multiple let's see, where's the divergence point? After the divergence point, have to say which way to go on each branch point.
Well, there could be more than one divergence point as well.
No, there couldn't. There's one first divergence point.
Well, there's one first. Well, that's fine.
Once it's diverged, you're off the map. Right? Once it's diverged, you've got to then say in every step what's going to do.
Fair enough.
Here, you see some of these have diverged much earlier. So if we say here, gosh, how do we figure out the first difference? Oh, I know what we do. Well,
I mean, A, B,
they're all the
this
same
is
number.
obvious, but A, B, you have no choice but to go to B, 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 B. And then after that, you do have a choice. So it's obviously going to be, it's not going to be the second.
So
Yeah.
let's just say first position
Or the second
of
position.
false of N. Okay, so let's take that's going to give us all pairs. Okay, so this is where the divergence points are, if there is a divergence point. Oh, right, and those are the diagonal elements. That's just basically a copy of the same thing, I suspect. Oops, no, that doesn't work. Okay, but in any case, that shows us the divergence points.
Yeah.
So homotopic equivalence. Let's see. What are these events that sort of go to a different branch pair?
Well, that's what I've been asking. I mean, it would. I think it would be helpful if we tried to think about it mathematically.
Well, in terms of the token event graph, okay, so here's the question. What is path-to-path evolution in a TEG?
TEG, yes.
Token event graph.
Yes, token event graph, yes. I didn't know we were calling them that.
I just made, I've been doing my own notes.
Okay.
But,
yes.
Okay. So let's draw a token event graph. Let me just find a convenient token event graph. By the way, has somebody updated the physics project guide page to include token event graphs? Could you maybe chase that?
No. Yeah, sure.
In general, we add a physics related thing to the function repository.
Yeah.
We should
Where does it go? Where does it go on the
Okay, so this is
physics
really bad.
website?
So here,
Yeah.
this is just tagging in the function repository
Yeah.
that
Yeah.
it's physics project related.
Yeah.
Okay, and then let's see if I say token event graph. Oh, what the heck? I thought it was in there.
Didn't Nick say that he had put it in there?
It is in there. It's just not linked. It's not been successfully tagged.
Okay.
That's super annoying.
What does that mean? How can that be the case?
Because it
Basically,
wasn't in the submission notebook somehow.
okay.
Oh, wait a
Okay.
minute. What the heck is this? Something is very wrong here.
Let's see.
Why is token event graph under not ready? I'm super confused. Well, let's see if this works. Okay, I'm irreducibly confused. How can it be in there but not showing up anyway? Okay, so we got a token event graph like this. What is oh my gosh, you see a path is not really a path. A state's path
Yeah.
is a collection of tokens.
Yeah. Wait. State's path is a collection of tokens. Yes.
But we can imagine for different tokens,
Sure.
let's pick this one here. What the heck is going on with different paths in the token event graph?
Between tokens.
Yes, presumably.
Well, yeah, I mean, it's homotopy between paths. I mean, in some ways, isn't it just an equality between some set of events? Yeah.
Those are different paths with different numbers of events.
Yes.
And what are you claiming? You're claiming,
Well, what I'm saying is that these different paths for the token event graph have these different events. And so you could think about the homotopy between the paths just by talking about the events, though it might not just be one, it could be several, and the number could be the number of events in each path might differ, but there's still some way of basically describing some set of events as being the same in that the events lie on paths between tokens, right?
yeah, but why don't you have to then say the tokens are the same too? Why aren't you back to the same story of just saying that the paths are equivalent?
Well, that's interesting. I wasn't thinking about that. Saying that the tokens are equivalent, but what are the tokens in this case?
Well, the tokens are the individual things that are getting rewritten.
Right. But we don't want to say that they're the same. I mean, they
Well, it's just the
respect.
same thing that in time evolution, things aren't the same. They're merely
Yeah,
related.
good. Good. Right.
So the issue is there a sideways evolution?
A sideways evolution.
Given the histories, the sideways evolution is jumping across branch pairs, is essentially critical pair lemmas.
Yeah, okay. When you say evolution, do you mean evolution towards
I just
something
mean
of
a
interest?
process. Look, I mean, here's the difference. The difference is, right, okay. In ordinary time evolution, there is a fixed rule that gets repeatedly applied. Though, in the Rulial case, there could be different rules. Okay, whereas in sideways evolution, there are typically different this event. Let me think about this for a second.
Are they just different entailments?
No, you got to take a path to a path, and that's a different thing.
Oh, yes, but they're paths between entailments.
Yeah.
Yes. Well, yes, they're common entailments.
But typically, this event leads to this event. Okay, the basic point is, Rulially, it's all the same. Because there exists a rule that goes sideways.
Okay. Yes. This will be an important point for the Ruliad project. Yes.
Right.
Right. Yes. 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 There are sideways rules. That's right.
Right.
Absolutely. Good.
Although
yes. Okay.
those rules may be complicated to find, and they may not lie in the same you may have to go far out. Okay, example, multi-way Turing machines.
Okay.
You can, okay, the
Well, yes,
sideways rule.
this was the topic of my summer school project, right? I called this a two machine.
Okay.
This is the whole point, is that it's a two machine. It's basically its computation is that it has some rule that goes between rules. Yeah, right.
Okay, fine. Oh, that's interesting. The sideways rule is not a simple Turing machine.
That's right.
It's right, even though it is computable.
Right. Right. And the example, for what it's worth, the example was thinking about for complexity classes completeness. So if you have NP complete, for instance, you have some say some problem and some solution, and you solve it as a Boolean satisfiability problem, say, or you solve it as a vertex cover problem, so to speak. Well, those are two completely different computations, but because it's NP complete, you know that you can do it either way and it leads to the same result. So there should technically be some proof that you can translate from one to another, and you could represent that as a two machine. That was an example.
Okay, that's a good example. Right. E.g., the translator between P complete or NP complete problems. It's going to be easier for P complete, I suspect, but right. I mean, segueing to the Rulliad for a moment. The whole point here is, right, the reason that the Rulliad is the infinity groupoid is because it always has sideways transformations.
Well, not just sideways, but then there are transformations between those sideways transformations, etc. Sideways, sideways, whatever
Yeah,
you want to,
I
whatever
know,
cute
I
name
know,
you
I
want to
know.
give it. Yeah. Yes. And now we're quite far afield from, I mean, that's the thing, which is Hammurabi type theory, they get into this, but has any reckoning really has anyone really thought about what this means in terms of computer science, computability? I don't really think so.
Well,
what
right, but I
exactly?
mean, one question is, are there obstructions?
Well, yes.
Right.
And this is my physics project research. This is the whole point, is to try and understand the fundamental groups and the homotopy groups, and to try and understand the genus of these spaces to see if there are obstructions. And in the end, as I said before, I think that there will be lessons in terms of computational irreducibility, in terms of there being obstructions. You get
Yeah, no doubt.
yeah,
Right.
yeah.
But the question is, what the heck? I mean, in the end, PCE implies that there aren't, other than the black holes, basically, there aren't going to be obstructions. But there may be big humps to get over, if that makes sense. There may be
Yeah. Well, in obstruction, when I say obstruction, I mean a topological obstruction. All it means is that it takes longer to get somewhere. Maybe there's some circuitous route and a shorter route isn't available. It doesn't mean you can't get there.
Okay, fair point.
Yeah, so that's
So there's some,
so you can, I mean, you have irreducibility, but you still have PCE. PCE
Yeah.
still holds. Now, this whole matter of black holes, how that fits in, I'm not quite sure. Where you're somewhere and the computation is reducible, you can't get out. By the way, this notebook, I think I was under the impression in the beginning that we were taking notes and this would be something I would kind of show to Nick, but now this seems like it's kind of the makings for a blog post.
well, I'm just putting this in our standard place.
Okay. No, but I mean, in terms of the,
Oh, you mean my workflow?
In terms of the purpose of this or what we're doing right now.
Yes. Yeah. This is my workflow is I'm trying to build up what I need in order to write about mathematics.
Yeah. Okay.
But the thing that I know I need, look, I really want this empirical stuff from the MetaMath project because I think something is going to be discovered from that. I would love to have a toy example of how entailments work in some simple case.
Okay.
And we've got to understand the relationship between hypergraphs and expressions. And by the way, that second thing is also very related to the whole multi-computation language framework.
Yes. The only thing about MetaMath is that it doesn't tell you anything, because part of what I'm interested in understanding is how the mathematics that we use, how we can come to understand the way in which we have arrived at that and not some other kind of
I know it's going to be I know,
but with MetaMath we don't get any of those arbitrary axiom systems.
Don't worry about that. It's going to just be
well, okay.
It's going to be what theorems we choose to look at.
But they'll all be sampled from MetaMath. That's my concern.
Don't worry about it. Let's just see what we sample first.
Okay. Well, I've had in mind this kind of this way of doing it where we start to just take random samples of random axioms and see what happens.
Well, that's a different project of trying to look at that as a toy example. But now
that's fine.
My question
is, if for the blog that's what you want.
Well, I want both things. I'm going to want both things in the end.
Okay.
But I mean, let's just hold on. The question is, what is the mathematical observer like? Okay, so we know. Oh boy, I started writing a few days ago my crazy what it's like to be a computer essay. Did I tell you about this one?
Has it been written or is it some draft?
It's just notes.
For what it's like to be a computer. No, you haven't told me about it. Interesting.
It's I tested it out on some kids today.
So what's it like?
What it's like to live a computer life.
Oh, well, that's different from what I was thinking you.
No. This is what it's like to be a computer. But living a computer life is the time from booting up to it being shut down.
Yes.
When it's shut down, it dies. Time stops.
Yes.
Its life is its anyway, and what's really quite amusing, I mean, I was testing this out on these kids because I wanted to see what they would do with the, how does the computer figure out if it has free will?
Yes.
What a mess. What a mess. It's lovely. I mean, it because the computer is just sitting there cogitating with no outside input, and it can do that. It's got all these processes running, all these threads. I mean, I was going to write something about the realistic case, like a computer with a real operating system and so on, right?
Yes.
Because that's kind of like a messy human, so to speak.
Yes. Yes.
And it's really amusing. It's so similar. I mean, it really is not. And I love the kind of the notion of the immortal soul.
Does that arise in this story?
Of course it does. The immortal soul of a computer is the engram of the bag of bits that represent the state of its memory.
Very nice. Very nice. Very nice.
And clearly it's independent. The soul of the computer is clearly independent of the hardware of the computer.
Yeah. Right.
Now, it's also the case, the one difference is reincarnation works differently for computers, because a single body has a new mind put in it every time the computer reboots. The computer lives a new life every time it's rebooted. So that's a little different. And education works a bit differently for computers, because the boot sequence basically is the education process.
How did the kids respond to this? They liked it. They
were amused. They were amused. They were they kept arguing. Surely you can tell that it doesn't have free will, or it does have free will.
Oh,
relative
good.
to humans.
That's good. That's good.
Um,
By the way, have you ever read Christos Papadimitriou wrote this novel called Turing, which is, these people have some computer and it comes with, basically the computer has this kind of character who is Alan Turing, and Alan Turing kind of explains what computation is in this kind of cute way. I don't know if you've ever come across that.
No, I haven't seen that particular one. It's that the same guy who wrote the Logic comics or whatever.
Yes. Yes. I don't know where he finds the time, but in addition to all the other work he's done in computational complexity theory, Papadimitriou writes these kind of cute comics and novels.
Huh. Well, anyway, the main reason I was going to try and write this, what it's like to be a computer thing, is because, if we're writing about consciousness and so on, right, people say, the question is, do computers already have consciousness?
Well, I suppose it won't that just come down to your definition?
It might. I mean, I think that there may be some slightly complicated things about sensing physical space and so on. But anyway, I mean, I was just playing with this. It's my precursor to writing my grand correspondence of our stuff with philosophy.
When you say grand, you mean a grand blog or a book?
Oh, I don't know.
Okay.
I mean, look, this blog I just wrote is 70 pages. So, I mean, it's like these things. Look, I think my scheme of collecting blogs into books is the best scheme.
Oh, it's great. Yes. I mean, I was wondering maybe last week or so, I thought, Stephen's putting so much effort into these blogs, these recent ones especially. I really hope he monetizes this. It really makes sense to monetize it. And a book is a great way of doing it, especially since you have Page and the whole apparatus for doing it pretty quickly, it seems. So
yes.
It's great. It's great.
No, but I mean, the thing, I think there'll probably be a multi-computation one. And, anyway,
Okay, now,
back to this.
What's
What
a
is a
mathematical observer like? Oh, yes, I see how we got into that tangent. Yeah, what's a computer? Yeah, okay. What do you mean, what is the observer like?
Well, a physical observer is computationally bounded and sequentializes time. Those seem to be, and physical observer, okay, so a physical observer has various characteristics. It computationally bounded, sequentializes time, and is subject to pure motion.
Okay.
It can move without change in space.
Mhm.
So now the question is, what is a mathematical observer like? A mathematical observer, so by sequentializing time, a physical observer is forcing certain threads to be equivalent. So a mathematical observer are they, in effect, are they doing the univalence axiom effectively?
Well, that's interesting. I was going to say that they impute semantics and that they recognize, say, identity or equality. Maybe that's what you're getting at as well.
Yeah, that which is equivalent is equal.
But what's equivalence? We haven't discussed. I mean, I understand it in univalence.
Well, equivalence in this case is entailable, is mutually entailable.
This is just a sideways. This is the sideways homotopy.
Yeah, right. This is.
Yes. So I mean, a mathematical observer. This is all kind of the same thing, at least in homotopy type theory, right? Which is semantics, equivalence, equality.
Well, this is saying the sideways observers being the same is the same thing as saying sequentialization of time, I think. Yes, because otherwise there are many threads of time, right? That's saying this is equivalent to there is a single thread of time. That's the physical way of saying that, I think.
Physical? Or
yeah, physical. That's the physics analog of that.
Wow. Okay. Yes. Yeah. Okay.
So two different paths, i.e., it doesn't matter how you prove things.
It doesn't matter.
They're two different paths.
It doesn't matter which proof path you select. Of course, it matters how you prove things. Yeah. But it doesn't matter which proof path you select.
Right.
Yeah.
That's a little different from the physical observer is coarse graining. Physical observer coarse grains across threads of time. Right?
Yes. This is better, I think. Better in the sense that it seems much nicer to be establishing proof equivalencies than to be coarse graining.
Well, maybe so. Physical observer coarse grains across threads of time. And look, it's the same damn thing. The mathematical observer coarse grains across proofs. They don't care which proof it was. It's still true.
Is that what coarse graining is, though?
I'm not sure, and it may depend on causal invariance. It may depend whether the thing is ultimately equivalent. But it's not self-evident that, okay, so fact about mathematics. Okay, mathematics is built on theorems. Each one can have many different proofs. But the building blocks of mathematics are theorems. Just like, and so I think the analogy, the building blocks of physical experience are classical observations. Because this is, this is quantum mathematics, basically. The idea that there can be different proofs. What is the effect of different proofs? What's the mathematical uncertainty principle? I think the mathematical uncertainty principle is that if you think about parallel transport in proof space.
Yeah. I was just thinking about this earlier today. Okay, go on. Yes, let's talk about holonomy. Homotype type theory doesn't get into this at all, but this is something I'm hoping to do with Xerxes. Yes, okay, go on.
Okay, so parallel transport in proof space is asking, it's making diamonds, basically. Yeah, causal invariance, if there is confluence,
Yeah.
there is no curvature. Slow confluence, or none at all, gives curvature. So in other words, the inequivalence of proofs, the fact that you're getting to different places, the fact that you're visiting, you're doing different mathematical sightseeing on these different proofs.
Yes. Yes.
Is the statement of curvature. That is, you see different mathematical sites on these different proof paths.
Well, now we get into the analogs of energy, but also I think that this is important when we recall that the observer is computationally bounded in some way as well. I think that
yeah, that's probably right.
This is important, I think, for whatever the exclusion principle or the uncertainty principle is for
You're right.
mathematics.
You're right. If the distance between proof paths exceeds the extent of the observer in proof space, then one will see quantum effects, basically.
Right. But we have to say what that means metamathematically. Metamathematical quantum effects. Or mathematical quantum effects.
No, it's probably metamathematical quantum effects. So, okay, what does that mean? That means fundamentally what that means is you don't know what's going to happen for a while, so to speak. There are distinct outcomes. It's like virtual particles. Okay, so what is the analog? So that means
What is the analog of?
I think the answer is, I
Yeah.
think it's this. I think it's that you get two otherwise incompatible statements. Yes, I claim it's the following thing.
Yeah. Okay.
It's that on two different proof paths,
Hmm.
you end up with two incompatible statements for a while. I think that's the analog. And then eventually they merge. But for a while, they're incompatible.
Okay. By the way, in physics, there's this amplituhedron that Arkani Hamed has come up with as a way to try and short circuit the need for virtual particles. Has this idea come up at all in the physics project?
Yes. It's a dual, it's some kind of dual thing where you're thinking about scattering as
Right,
the fundamental thing rather than particles as the fundamental thing.
right.
And yes, I think there's a direct analog of it.
Right.
And this hasn't been worked out yet.
Okay.
Um,
Well, that would be a good summer school project for someone.
it would
But
be.
I was thinking about that for this as well. Equivalent that is. Well, what's the equivalent? We haven't talked about what's the equivalent of scattering. Now that we have this idea of virtual particles.
Well, scattering is just, I would say that the scattering is to think about everything in terms of entailments rather than everything in terms of, I mean, the scattering process is two entailments lead to other entailments rather than two particles. That's the scattering. It's an event-based thing rather than a state-based thing. I think that's what it is.
Okay.
I think the amplituhedron is just, think about, it's an event-centered description rather than a state-centered description.
Okay.
I have a relevant question. Do you understand intuitionism?
You mean like Brouwer and
Brouwer,
in the
yes.
kind of mathematical interpretation? I've struggled, admittedly, to try and kind of disentangle that from constructivism and from how kind of Martin Luff's intuitionistic type theory has made its way into HOTT. Because I really just care about the HOTT. And it's kind of like when you were working on multi-computation, there's this kind of prehistory, but you're not sure how relevant it is. That's how I feel about intuitionism as well.
But you see, one of the things I think is interesting there, I think this law of excluded middle, removing the law of excluded
Yeah.
middle is a very technical point. I don't think that's really the point. I think there was a bigger philosophical point.
Hmm.
But because, one of the claims is that all of the stuff we're talking about here in the end, the mathematical observer goes much further. It doesn't matter which proof path you go on. You are coarse graining in proof space. And actually, you don't really care about proofs at all. You care more about the structures that proofs. Yeah, I mean, it's like in physics. Okay, it's the fluid dynamics versus the molecular dynamics. Okay, physics. So it's kind of like the fluid level description.
Yeah, but it depends on how you want to describe this, because that could still be a sideways proof. You see, it's not necessarily that the
I'm going to
proofs
claim
don't.
that the fluid level description is talk in terms of objects. Talk in terms of, it's not really objects. It's really concepts, not instances, i.e., points and lines as concepts, not their atoms, so to speak. And I think that's analogous the heck is that analogous to in physics? I mean, in physics, somehow in molecular dynamics, you have to be talking about particular molecules, where in fluid mechanics, you're I don't know. I want to try to figure out what is the higher level description of mathematics that is not in terms of this sort of the formal structure of proofs and axioms, right? So the higher level description of mathematics is in terms of human relatable constructs. This is also the question of, is the continuum hypothesis necessarily true or false for a human observer? There might exist a real reference frame in which the continuum hypothesis is, let's say, false.
Well,
but it might be the case that
that
is not a human accessible reference frame.
What would that mean? When you say not humanly accessible, is it in a black hole?
No, it means that to maintain that view under entailments, okay, so a non-human accessible reference frame is one that is shredded by entailment evolution.
Shredded by its own entailment?
Yeah, but by the evolution under entailment. So, in other words, okay, so if you think about general relativity, okay, there exist, let's see, if you try to set things up so that you have a space-time gravitational field that produces a naked singularity, for example, you have to go to lots of trouble. It's the same thing, okay? So analogy, a non-thermodynamic coarse graining. Right, you could imagine a non-thermodynamic coarse graining, right, in which you are carefully, elaborately sculpting the way that you sample the molecules so that you can tell what initial condition you started from, right? You can distinguish initial conditions. Okay. But we know that that becomes arbitrarily difficult. The phase fluid becomes arbitrarily, sort of complicated.
Yeah. Okay.
And so the claim would be that in mathematics, something analogous would happen. That is, look, the coarse graining that we're talking about here is a concept coarse graining. We want to, okay, so concept coarse graining e.g., the concept of integers. Right? In the end, we've got an axiomatic system, but we've got the concept of integers.
Mhm.
And we can try and understand how that could arise from molecular dynamics. But we still have an intuitive, what does it mean? What is the intuitive concept of integers? It is a description frame for integers. It's an intuitive notion of integers, which doesn't have non-standard arithmetic, doesn't have large cardinals, et cetera, et cetera, et cetera.
Right.
And the question really is there fluid dynamics or is it hypersonic flow? And is it the case that as you start working out the consequences of arithmetic, that you can survive in the, walled garden, not very walled, in the pleasant spot that is something like the ordinary integers without being thrust into large cardinal land? Right? With entailments,
Yes.
given an intuitive description of the integers, do entailments lead to non-standard messy stuff? Okay, and the point here is that the intuitive description is a coarse graining.
And what is that kind of a defense against falling into this kind of shredding territory?
Yes, I think so.
Yes.
The intuitive description is a coarse graining under which there are many specific instances. Do they all lead to similar coarse-grained results or not? And that's the same thing as thermodynamics. Right, and so the question is, as you see can you preserve the notion of integers as you start working on the consequences of the theory of integers? Does it work to preserve that concept? Well, it does, more or less. What's another example? When do areas of mathematics kind of lead you off a cliff?
Well, it depends on what you mean by a cliff, but anything asymptotic in some way does.
In what sense?
I mean, as you were saying, with large cardinals, I mean, it's basically, or if you're thinking about the ordinals, I mean, just these higher, the transfinite, yes, that's kind of a cliff. But even getting arbitrarily small, or maybe how about the transcendental numbers? Well, maybe that's similar to what you were getting at before.
I mean, the question is, are you inexorably led to large cardinals, etc.?
Well, but what does that mean exactly? I mean, we're mathematical observers. Our mathematics, that we have cardinal arithmetic, for instance, we have transcendental number theory. But
I know, but the
we're
question
okay.
is, are you, as you look at the entailments of things, look, the question is, can you preserve the coarse graining? Or do the trajectories under entailment, right? This is the question. Can you preserve the coarse graining? It's the same story as in, it's the same as thermodynamics. There are certain things you can preserve. You can preserve the gas laws, but not some detailed statement about motions, about microscopic motions.
Yeah, okay. Okay.
So the question is, what kind of thing in math can you preserve? And my claim would be human mathematics. Okay, the claim is human mathematics is the stuff you can preserve. That's the math that humans do. Whereas
Yeah.
automated theorem proving includes stuff you can't preserve. Down at the atomic level, you're dealing with stuff you can't preserve. So then the question is, how do we characterize what is that stuff we can preserve? How do we characterize that? What's the analog of general relativity? Doesn't help that we don't have a good analog of space.
Well, yes, that's true. That's why I've wanted to start. And I've started, though I have to really double check with Nick about this code. I've been interested in just seeing what analysis we can do on, known mathematical systems, and then do the same analysis for just random sets of axioms and try and see what behavior comes up.
It'll be the same. It'll be the same. You will not be able to see the difference.
But we're asking a question that it doesn't necessarily suppose that there's a difference, but we're entertaining the.
No, but
There's
it's
a
not at
difference.
that level. You're at the wrong level. You're asking, is there a difference between what water and air do? And the answer is no, there's no difference when it comes to the gas laws, fluid dynamics. Right, that's what you're asking. You're asking, can you see the difference? Could you see, if I show you methane, could you say, oh, that will be different? And the answer is you might be able to say methane will have a different viscosity, but other than that, you will be able to say nothing. The difference is, I claim all of these axiom systems have, well, okay, so here's the basic claim. The basic claim, there is a conceptual description. Okay, the claim, major claim. For any non-trivial axiom system,
Right.
there is a conceptual description.
Yeah.
That is similar.
So you're saying at the fluid dynamics level, it's PEC. It's PEC at the fluid dynamics level.
PCE.
Sorry. Yeah, so maybe in Spanish or something. It's PEC.
Right.
Anyway, okay. Yeah, sorry.
No,
Anyway,
I think it's a different phenomenon, actually. I think the universality of, no, I don't think that, actually. I think the universality at the fluid dynamics level is a consequence of observers interacting with multi-computation. It's a consequence of finding those kinds of reducibility,
yeah, right,
that are associated with our kind of observers. Now, we don't really know we've just talked about what our kind of observer for mathematics is. And the point is that our kind of observer for mathematics, okay, so the mathematical observer can only handle certain overall concepts, not atomic details, just as the physical observer can only handle overall features of space,
Right.
not its atomic details.
Well, now I'm beginning to really appreciate the kind of distinctive character of multi-computation and this fourth paradigm. Do you think that it would be appropriate to actually name something like PCE, but for observers and for this fourth paradigm, something that's distinct?
Yeah, probably.
Because now it's very clear that this is really what to test. I understand now. It's not about necessarily the axioms. This is what was, I mean, you did this like almost 20 years ago. It's now looking at these different levels at the analog
Yeah.
of the molecular scale,
Right.
and at the
So
analog of
the
the
whole
fluid
point
dynamic
is,
scale.
it
makes
could
sense.
be,
Yeah.
as my wife has been telling me for 25 years, that the whole idea of axiom systems is just a crazy modernist deconstruction of mathematics that was on the wrong track.
What a great I told you so.
Yeah, that's one of the more abstract I told you so's. But anyway, so
Very interesting. Very interesting.
but
But it seems as though, unless looking over all the notes that you've taken, it's more clear. Have we really defined the distinction between the molecular and the fluid for mathematics or for metamathematics?
no, we don't know.
Okay.
This notion of overall concepts. Okay, so look, in physics, we have an understanding of what it means to think about space, its uniformity, et cetera, et cetera, et cetera. In mathematics, and we have a notion of our extent in space, a meter, whatever it is, right? We have no sense of our extent in proof space.
We don't know our extent in proof space. Well, what does that mean exactly?
It means you've got two different proofs.
Yeah.
And as far as you're concerned, they're equivalent. They're the same. You just don't need to distinguish them because you are conflating.
Ah, yes. Oh, so our extent in that kind of space. I mean, that's just like our n machine level, or so to speak, as I would put it. The extent to which our computational capabilities, and I suppose just the sophistication of mathematics and computation, allow us to actually establish those equivalences, which is going to be bounded at some level.
Right.
Alas.
So I mean, the point here is there's a certain coarse-grainedness in proof space is the stuff a human mathematician doesn't need to bother to describe. Right? In other words, if you're making a proof, if you as a human make a proof, you just make a general statement. Just make some general statement, some somewhat general statement about something. You don't need to atomize it.
So you can plot something over R2 and you just call it R2, right? Or you don't need to know the trillionth digit of pi or what have you. You can still do math.
Yeah.
Nonetheless, even though you don't know. right? I mean, we kind of dance over the reals all the time, every day.
Right.
Right.
E.g., not really understanding the reals. It's a good example. So that is the coarse graining that human mathematicians do. And that's what, as we try to do it with automated theorem proving, that's what we shatter. It's like atomic mathematics, so to speak, molecular mathematics.
Mhm.
Now, the question is there a level of operating on this stuff? So I would claim the high-level mathematics, human-level mathematics, is like computational language versus machine code.
Yeah, that's fine.
Right, but the important point there is computational language is a human-built thing. It's intended for humans. And it elides.
Mhm.
What's a little different is that computational language actually does implement something. And okay, the basic point is in computational language implements a definite machine path in machine code. But it's close enough to our intuitive notion
Right.
that it's an okay proxy. And so that, in a sense, has to be the goal of a formalized mathematics system. In other words, it doesn't really matter that, so, a formalized mathematics system should take a human level description and give one instantiation of it.
Okay.
And if it ends up in a different human level description, that's sort of chaos theory in math. Right? In other words, most of the time, it won't end up in a different description. The fact that there's computational irreducibility and thermodynamic-like behavior is what leads the close enough thing to work for computational language, I would claim.
Okay. Yeah.
And it's the same thing. So what I'm saying is the butterfly effect, right? In other words, if it is the case that one formalized math system will give a different result than another formalized math system, it's kind of the butterfly effect for mathematics.
Does that just mean dependence on some initial condition in the machine code?
Or some detail of the machine code. I wasn't really meaning initial condition.
Well, I know, but the analog of
right, it's a detail of the machine code is leading you to an intuitively different result. Whereas that mostly won't happen. Most perturbations at the level of molecules don't have any effect at the level of fluid dynamics.
Mm-hmm. Mm-hmm.
So one question undecidability in mathematics.
That's the kind of revenge of the molecular in some way, right? It kind of
Yes, it
creeps
is.
up.
Right.
Yes.
Right. I mean, so undecidability is rare in human level math. because it requires that molecular / quantum effects survive essentially arbitrarily long.
What's an example in physics, by the way,
Of what?
of that?
Of undecidability?
Yeah.
I mean, a good example is the ground state of a generalized Ising model. In other words, given an energy function for an Ising model with a bunch of spins up and down,
Yeah.
what is its ground state? And that problem is equivalent to the 2D tiling problem, which is undecidable. So you ask, what does it actually do in practice? If you have a material set up that way, the answer is it takes an infinite time to get to its ground state.
I see.
It just flaps around. In fact, the very practical things, I've looked at this for actual chemicals. Okay. It's kind of amusing what happens. You say, well, the thing should solidify. Okay. Actually, it becomes a blob of tar-like stuff.
Wow.
That's what undecidability is like in the chemical world, so to speak, as opposed to it lining up perfectly as a tiling as a crystal.
By the way, do you have some kind of ATP ambition in mind for Wolfram language as you do all this? As people are getting more interested in Coq and Lean and Agda, et cetera, et cetera.
Well, I know, but I'm trying to understand one of the things from this is to understand what the point is, because if what's happening is they're tooling off into some kind of, they're sort of climbing down a volcano. It's like, who cares?
Climbing down a volcano.
Climbing into a volcano.
The climbing into a volcano in what sense?
Well, if what's happening is they're just going deeper and deeper into something where they're just going to melt.
What what do you mean by melt?
Well, what I mean is that what they're doing could be something that humans fundamentally don't care about.
Ah, I see. So they're wasting resources mining the molecular.
Yeah.
Yeah. Okay. So they're going maybe in the wrong
and direction. It could be that the right thing to do is to build a computational language to represent mathematics and to try and humanize the thing, rather than to try and dig down and turn it into, and understand the sand.
Right. So you want to invest in, the kind of pragmatic commercial lesson from this might be, you can invest in making it easier at the fluid level and maybe have something in place for when the revenge of the molecular does creep up, though it might not be that important.
The problem that we have right now, the practical problem we have right now, is the representation of proofs. Well, there are two practical problems. One is the human level representation of pure mathematics, okay, which is a big piece of work. I mean, I've written about this. It's probably 1,000 functions we need to build for that, which is not out of range. I mean, we've got 7,000 functions now. To build 1,000 more is not crazy out of range, right? That would represent most of human mathematics up to the present day.
When do you want to do this?
Well, we've been doing it gradually over the last few years. We tried to mobilize the mathematics community about, what was it?
Okay. Yeah.
And we didn't really succeed. We succeeded in getting the formalized mathematics community interested, but not the mathematics community. And I'm afraid that this kind of shows us why. I mean, to the mathematics community, the formalized stuff, to most people, has missed the point. And what we're trying to understand now is, why is that true?
And that they might basically be right. That it doesn't matter to them that much.
Yeah.
Right, but why? But they don't know a different thing. They don't know why.
Right.
They're kind of taking a gamble because they don't know, but we can kind of make their argument better for them.
Well, yeah. I mean,
Yeah.
but it's like saying, if you study literature, or if you're a writer of things, what's the right analogy? Um, if you're an artist doing paintings,
Okay.
do you want? I don't know what the right analogy
What
is.
do you care about the exact concentrations of the different colors when you're mixing them or something?
Yeah, it's that kind of thing.
Or
Right.
like you're a musician and do you care how close it is to being a perfect F sharp or
Yeah,
something
that's
like
right.
this?
That's right. That's right. How? Yes, a painter. To what extent does the painter care whether that, whether the trajectory of that bristle of their brush does this or that?
Right. And you could have some automated painting assistant that tells you your precision to, 10 significant figures or something. Would it
Right.
matter? Would that be what's separating you from
Right.
Da Vinci?
Is the bristle motion, you know, the um
Yes. Okay, this is a humorous analogy. Yes, I understand.
bristle motion in painting versus
Oh gosh. Good thing this is basically just for you to read.
well,
So
it'll be out there, but people can but that's I don't know. I mean, this is a um yes, that's the question. And occasionally, right, in this analogy, a sufficiently fast brush stroke, fast and long brush stroke, might care about bristle motion.
yes. Yes. Yes.
But such brush strokes will be rare and usually aren't the point. But I mean, the question is, what is the way to science-size the high-level description? And it's possible that what we're doing with computational language is about as good as you can get.
Hmm.
But it would be nice to have a global theory that looks like general relativity, for example, that makes general statements about, I mean, well, look, the analog of general relativity is clearly something about the density of entailments versus curvature. Let's see, the curvature of shortest proofs. So I suspect that one statement is kind of the singularity theorems, that the density of entailments eventually leads you to lumps of decidability.
Okay.
I mean, that's the extreme version, that you get closer to decidability. Well, okay, so Einstein equations and metamathematics, or AKA gravity and metamathematics. So basically, the presence of lots of entailment, AKA energy / mass, leads to deflection of geodesics leads to focusing of proof paths, i.e., not wandering as far afield in metamathematical space i.e., sticking closer to the point. So this is saying that the presence of, there will be fewer very divergent proofs. If there are more entailments,
Right.
if there are more proofs,
Yeah.
there will be fewer proofs that can wander far away and end up with
Sure.
very different looking. So in
Sure.
other words,
Yeah.
math will be more focused if there's a higher density of entailments, i.e., so you can get back.
So
on track
what's
more
an
easily.
example of this, like linear algebra or something, or a study of matrices where you can go between that and groups and you can come back? I'm trying to
Well,
think
no,
of
I think the answer, okay, so the thing would be,
maybe geometry. I'm trying to
no,
think
I
of
think it would
something
be
where,
number theory. I think the
well,
case where
okay.
you get to wander far afield, probably number theory is a case where you can wander far afield. Because there are not so many local cross connections.
Well, yes. I was thinking of cases where you don't, not necessarily that you don't wander far afield, but that there's a high density.
Yeah, I suspect universal algebra.
Yeah, or graph theory or something
Not
like
sure
this,
about that.
where there's different, where you can easily translate between that and some other area of math quite
Has more
easily.
gravity. Universal algebra has more gravity. Therefore, the GD6, therefore the proof paths
Yes.
stay more concentrated.
Yep. Yep.
And eventually there are so many proof paths.
Oh no. Yeah, we discussed this, I think, last time. Yes, there's so many that
that it becomes a black hole.
yeah, right.
Becomes a decidable black hole.
But do we have we don't have anything like that, do we?
Sure we do, Boolean algebra. I mean, it would be lovely to see this. This is why I want to see this empirical metamathematics. I mean, if we could see that the number of proof paths is much higher for Boolean algebra than it is for number theory, for example.
Yeah. Yeah.
Then we would be able to essentially prove this.
Okay.
This is going to be a very bizarre document. This is going to be something, I think it has few analogies, because what this is, in a field full of precision, this is a giant pile of intuition, which is very odd.
Well, this is what happens when you approach it from physics, right?
Well, yeah. Yeah, because there is intuition in physics. But I mean, there is in mathematics as well, but people don't admit it as much.
Yes, that's what I mean. That's the kind of reputation that physicists have amongst mathematicians.
Yes. I think this is getting closer. I think it's getting more easy to understand what.
Yes, I mean, well, applying our own method to what we just said, I mean, it never seemed as though we really encountered something we couldn't fully explain, but we could have maybe just avoided those and focused on what we could explain. But
Well,
the number of lingering questions is progressively diminishing.
right. So undecidability, the reason it's rare, also, we tend to concentrate on math for which we can form a conceptual description, which is precisely the human level, fluid level math, basically.
Mm-hmm.
And we don't look at those aspects for which we can't form a conceptual description.
I mean, some do, but it's relatively ignored.
Well, I mean, in the whole ruleology business, we're just like front and center. I mean, ruleology is not like math in that respect. Ruleology is full of undecidability.
Yeah.
I mean, what's interesting about ruleology with respect to math is the type of intuition. Intuition of ruleology is much more like the intuition of natural history than it is like the intuition of mathematics. In other words, things just happen, and they happen in certain patterns, but they're not, I don't know, maybe that isn't quite right, but it's a, ruleology is a great field. It'll be, I mean, I should have done this long ago of really naming it and breaking it off. This is going to be, I mean, I'm very enthusiastic about the human dynamics of launching this.
Yes.
All right.
Even from, I think having the names, it makes such a difference.
It does.
It doesn't feel as though you're just playing around, you know?
Right. Well, I do think that the probably the metamath discussion is probably, I think we probably reached the end of the metamath discussion, so we can just